So the last thing we want to look at in chapter 17 is called Solubility Equilibria and the Solubility Product, KSP. K is still our equilibrium constant symbol. The SP stands for Solubility Product. KSP can be applied to equilibrium when you have a slightly soluble salt. When you have one of these types of salt, it will dissolve in water and it ionizes. So here's an example of a slightly soluble salt, silver chloride. That is just a solid. These salts are solids. When you put it in water, the water will pull it apart into silver ions and chloride ions. Now remember, these are slightly soluble salts. They're not the very soluble salts that we would say would dissolve 100%. That's why these form equilibrium. If you write the law of mass action for this reaction here, the equilibrium expression is K. In this case, we call it KSP for solubility product because these are salts, not acids or bases. And they're slightly soluble salts. It would be equal to the silver ion raised to the first power because there's a coefficient 1 here. And the coefficient 1 here means this chloride ion to the first power. K is KSP and it's called the solubility product constant. A couple of facts about KSP. The KSP is constant only for solutions that contain slightly soluble electrolytes or slightly soluble salts. It varies moderately for very soluble salts, and it increases if you have the higher the ionic concentration is. So this concept will apply only to small concentrations. So we're going to first look at how to calculate the KSP from their solubilities. Now solubility, first of all, when it says solubility, it must be expressed in moles per liter or molarity. X, when we ice our problems, represents the solubility. So our X's in our ice tables are going to represent the solubility. Example 1 here in your notes says the solubility of lead 2 chromate is 4.3 times 10 to the negative 5 grams per liter. Now remember, solubility needs to be in moles per liter, so we need to do a conversion here. But it wants to know what is the KSP. So we want to find the equilibrium constant for this lead 2 chromate. First thing we need to do is convert the solubility to molarity. So 4.3 times 10 to the negative 5 grams per liter. We need to convert that to moles per liter. So we're going to use the molar mass to do that. We need grams to cancel, so we'll put it on bottom, and the molar mass, the moles go on top. So the molar mass of the lead 2 chromate, if you add that up, 207.20 plus 52.00 plus 64.00, that gives us 323.20 for our molar mass. So we're going to plug that in here, 323.20. And this lets our grams cancel and it gives us moles per liter, which is molarity, which is what we need for our concentration unit. So our molarity here is 1.3 times 10 to the negative 7. And this is what they're calling the solubility. Now remember, solubility is going to be what X is when we do our ice tables. So let's write our equilibrium reaction here for this slightly soluble salt. PbCrO4, and remember these are solids. They're going to form equilibrium when we put them in water. This is going to pull apart into the lead 2 ion and the chromate ion. These ions are aqueous. You don't have to write that, but all ions have to be aqueous. Now, if you ice your problem here, since this is a solid, just like with our water and our acid-base reactions, there's really no value that goes here. There's going to be 0 and 0 in the initial amounts here. But once you put it in water, it will start to ionize. So the shift will go towards the products. And since this is a 1-to-1 ratio, you'll say plus X and plus X. That means at equilibrium, the concentration of the lead-2 ion is going to be equivalent to whatever X is, and chromate as well is whatever X is. So the next thing we need to do is to write our law of mass action, because it wants the KSP. So KSP, according to this equation, is going to be equivalent to the lead-2 ion concentration raised to the first power times the chromate ion concentration raised to the first power. We're trying to find KSP, and the solubility is what X is. So we were told the solubility here. So I'm going to finish this out as equal to X times X. So KSP is equal to X squared. So we're going to plug in our value for X that we were told. KSP is equal to 1.3 times 10 to the negative 7 molar, and we need to square that. 1.3 times 10 to the negative 7, and we need to square it. So that's going to give us for our KSP and our answer 1.7 times 10 to the negative 14. So that will be your answer for your KSP. All right, let's look at another example. Your example 2 in your notes wants us to calculate the KSP again for silver chromate. So we're going to write our equation, Ag2CrO4. That's a solid again. It's going to form an equilibrium. Now when this pulls apart, the silver ion has a +1 charge. Notice there's 2 silvers here, so you put 2 silver ions. Chromate is CrO4 and has a -2 charge. Be very careful when you dissociate these so that you make sure your equations are balanced. Again, there's a 0 and a 0 here, and when the shift happens here, it's going to be +2x here and +x here because of the coefficients. That means at equilibrium, the concentration of silver is going to be equivalent to 2x. Concentration of the chromate ion is equal to x. So write your law of mass action. KSP is equal to the silver ion, remember, squared because of the 2, times the chromate ion to the first. And we were told the solubility right here. Remember, solubility is your X. So this is what we're going to plug in for our X value. So KSP is equal to, plug this in here. There's a 2x that plugs in here, and don't forget to square it. An X plugs in here, and that's to the first power. Simplify this out. KSP is equal to, this here is a troublesome area for some. Don't forget, you got to square the 2 and the x. That's 4x squared times x, and KSP is equal to 4x cubed. Now, go ahead and substitute your x in from the problem. You were told the solubility. So KSP is equal to 4 times 1.3 times 10 to the negative 4, and that's cubed. So cube the x and multiply by 4, and that gives you your KSP value equals 8.8 times 10 to the negative 12. Now you could be asked to solve for x instead of the KSP. They might give you KSP, so that's what the next slide is. Calculating the solubility x from the KSP, just going backwards from what we just did. So let's look at this one. This says the solubility product, now remember that's KSP, for silver chloride is 1.8 times 10 to the negative 10. Calculate the molar solubility. It wants us to find x here. You still want to write out your equation. This is your slightly soluble salt. Silver dissociates into the silver ion and the chloride ion. It's a 1-to-1 ratio. When you ice your problem, the solids have no effect on the equilibrium shift. There will be a 0 and a 0 here. This would shift to the products plus x and plus x. So that means silver is going to be equal to x and chloride is going to be equal to x. Write your law of mass action. KSP is going to be equal to the concentration